thing called a car, and we know that there are different kinds of car. There are Toyota, there's Honda, there's Honda Civic. Let's say there's Maruti Suzuki. These are all brands of cars, and like they all have the different types of cars, like all these brands. But we know that each car has something in common, and what is that? It's an engine, it's a wheel, it's something. So that entire concept of car is it is referred to as a class, whereas a particular car is called an object. So essentially you need to understand two things: what is a class and what is an object. So class is like a broader term. So let's say I say ki there are many books, okay, and there's this one particular book which I have issued. So a book is an instance of that class of like the book that I have issued, hands-on machine learning book. Let's say it is an instance of the class books, and it has all the attributes. An attribute is something that is used to define the features or define the qualities of that certain object. So, for example, in Python, how do we declare this? So we use something called class keyword. So a class keyword is used to declare a class in Python, and it is characterized by something called a constructor function. So a constructor function, well, that terminology is used in languages like Java and like other languages, object-oriented languages. Python is not so object-oriented. It supports everything, but this constructor function is called init function in Python. So we need to understand a few things here. Firstly, what is self? Then what are the inputs that are being taken by this init function? So an object is, well, something that is stored in the memory, right? And the pointer to that is contained by this self keyword. So that is what self means basically. So when you say self.brand, it essentially tells you key corresponding to the pointer self, it has a feature called brand, and that is being taken by this input of the init function. So there's something called init function. Then just to recap, there's something called an init function. Then it takes in different types of input. The first one is called self. That is a pointer to the class itself. And then there are all the basic attributes or keywords that you need to instantiate this class. So that will be so whenever you declare an object of this type, object of this class, for example, my car is an object of the class car, then this init function will be called automatically. So if I run the cell, this is connecting. That's all. So when I run this cell, what will happen is key this my car dot brand and my car dot model will get printed. So my car is gonna give you the pointer to self, and it will then access brand variable. So this variable, which is defined with self keyword, is called an attribute. So basically, attributes are variables that belong to a class. And why do we have these attributes in the first place? Well, they are used to store certain data corresponding to a class. For example, if we think of a car, what are the certain attributes that you can think of? It will be what is its brand, what is its model, how many wheels does it have, or what is the size of its wheels, or what type of suspension does it have. So these are all attributes of a car. Now, another thing that we need to understand is what is called a method. So a method is like a function that is pertaining to a certain class. So um, like let's say you have a car. So what all functions can it perform? Well, it can basically move forward, move backward. It can change gear. So all of these functions that are performed by a certain object, they are just called car. So they're just called methods. So corresponding to the object car, they will be move forward, move backward, change gear, and all that. So essentially, the difference between a function and a method is just that a method is for a particular class and it cannot be globally called. So to call a function, let's say display info, you will have to do the variable that has been instantiated with the object, that is my car dot the method name, and this is defined by the def keyword. So as you can see by the indentation, it is defined in the class itself. So there are two methods. One is the init, that is the constructor method, and the other is the display info. So that is what is called a method, and if I'll just run it, it will just display me the brand and the model that we have done it. So the next concept is encapsulation. So encapsulation is, well, sometimes you want to have some sort of access control mechanism. So let's say you do not want anyone should come in and change all the variables corresponding to a class, because some things are supposed to be private, right? For example, you are having a library management system. Now that is implemented as a full class in itself. Now there will be certain entities in the class, that is your student, that is going to be well, a teacher or someone. So everyone has different kinds of kinds of authorizations, right? So we cannot allow everyone to just call every single method, right? Not everyone should have the entire control of the library. They can use it, but they should not change anything. So what do we do to just a loose analogy here? So what do we do here is that we do not allow, we declare these variables or these attributes as private. So how is it done? By doing this underscore underscore. So this essentially shows us a private variable. So after doing this, what happens is that we only allow to change uh, these variables through this through a certain method, and that method is to be called only by a certain class or a certain type of entity. So in order to change cell.brand, I'm not using set cell.brand equals to some value. What I'm going to do is cell.set brand or set model. So that way I'm encapsulating all the attributes to a function, and that basically helps me to give, isolation to all the attributes. And essentially what I can do here is that if there is some logic that is to be implemented in this get brand or set brand, because these are very fundamental operations, so there's not much logic involved here. But if there were some complicated logic, I would be able to prevent anyone from doing something illegal in the function itself. So let's say if there's a move gear function. I don't want that someone will move the gear of the car from 2 to 4. I want him to first go to from 2 to 3, then 3 to 4. So by giving the person a function and not a variable, we can ensure that things go our way. So the other thing is called abstraction. So abstraction is like when you don't want everyone to like change a certain how blueprint for a class. So a class has very much well, here we are defining our own classes, so they're very simple. But when we go to perform certain operations in, let's say, machine learning, so we know that PyTorch has everything implemented, right? Now the implementation is so complicated that we cannot just go and change anything, right? So what happens is that they declare their methods, their objects as their classes as abstract classes, and we inherit from those classes, and we only modify them. So what happens is that everything, all the complex implementation is well hidden to us, and only what we need to see is seen by us. So this is done by the abstract base class ABC in Python. So using this keyword, you are able to declare an abstract class. And this abstract class basically helps you to declare certain methods that can only be overridden. So that way we are able to ensure that whatever object we're declaring, no one misuses it. So in this example over here, there's a vehicle class that is the abstract class for a car and a motorcycle. So what is happening is this car and this motorcycle, they both are calling this vehicle. So what is happening is this engine function is being copied into each of these with a pass argument, and we are just overriding the start engine. So because of that, the same function will be called differently by each class, and we are able to declare it simultaneously. Like we are able to declare it for both of them by just calling this vehicle inside the class. So the next concept is called inheritance. So inheritance is basically a mechanism wherein you have two classes. So there is a relationship of a parent and a child. So what happens is the children, they are supposed to resemble something of their parents. So what happens is all the attributes and all the methods that are declared by the parent will be copied into the children, and the children may modify it. So what happens is I have declared a vehicle class. I'm calling its init function and I'm calling its display info function. So by using this vehicle keyword inside the car, I can reference the vehicle class as a super. So using the super keyword. So this keyword allows me to access the vehicle class, and then all of these attributes and all of these functions can be copied and used up by the child. So what does this allow for? This allows for a design pattern wherein you can isolate your stuff. You can show a hierarchical relationship between the classes, and it just makes everything much more easier to understand. So what is happening here is like this init function calls the init function of the vehicle class, and this init function this display info function calls the display info function of the super class, that is the vehicle. So super refers to this the one class that it is inheriting from. So when I call display info, it shows me only the number of doors, right? But let's say if I were to just modify this and comment this out, only the brand and that would be it would get executed. Because why? I have just commented out this part. So when I do not reference the super part, only the number of doors will be printed. So what this allows for essentially is a design pattern wherein there's a hierarchy relationship, and that allows us for you can say a better understanding of our code essentially. Overloading is a term wherein you wherein you try to explain that, let's say there's the addition operation. So the addition operation will concatenate two strings if given as an input, but will add two numbers if they are given as an input to the addition function, right? So that is called so basically that same operator is working differently for like different types of like inputs that are being given to it, right? So what happens because of that is your this essentially like this is called operator overloading. So different inputs will decide how the function is being or how the procedure is going to be executed, right? So there is something called the similar concept is well displayed in polymorphism, wherein objects of different classes, their methods are used interchangeably across different objects, and this allows them for a common interface. So what happens here is that I have declared a function which will basically act differently for if it is a car or a vehicle, and it has not been defined in the car itself, but there is some sort of shared attribute that is there. For example, the start engine attribute, it is there for both of them. Okay, so what I do is I declare a function which takes in an input, and it will just call input dot start engine. So start engine has been defined differently for each of them. So because of that, regardless of the type of this data type of the input, it will get executed because the same method has been applied, and it will work differently. So it will print starting car engine and starting motorcycle engine. So an interesting like use case of this is when you have this function def. So what this does is this string function, it shows it is basically used for printing. So when you print something, this underscore string is called, and because of that, what happens is that like whatever is written in the underscore string procedure will get executed. So let's say I am a motorcycle, and I declare a similar function underscore string. Uh, well, I I am a car. So I've just declared it, and let's print this car motorcycle. So yeah, that way this string attribute, well, it is being overloaded, and that is an example of polymorphism that you can see. So now we'll move on to composition. So is a composition is well, when you have a has a kind of relationship between your objects. So let's say class A has an attribute has owns class B. So that thing is there. So what is happening is this car class, well, one of its attributes self.engine is another class. So that is called composition. So this allows for pointers to be shared, and you need to be careful while when there's such a relationship, because pointers may move here and there, and like then certain complicated situations may arise. So yeah, that is an example of composition. On the other hand, there is aggregation. So aggregation is wherein you pass that as an input. So here you were not passing this as an input, but well, there's only a fine line between aggregation and composition. In aggregation, you do not have control over the attribute that is from the other class. Okay, you only have what is being fed into it. That is the horsepower. But here in aggregation, you have a certain type of isolation from the the bigger class. So instead of passing the horsepower, that was the input for cell dot engine for that engine, you are giving it the engine itself. So that is how you do it. Basically, the difference between composition and aggregation is in aggregation you pass the whole object, whereas in composition you do not give the whole object, just the input to it. So in that way, aggregation is different. Now we'll move on to how we are using this, how we actually use this in machine learning. So I'll be taking the example of linear regression. For linear regression, you might remember there were certain parameters that we had, hyperparameters, namely the learning rate, the number of epochs that we want to learn it for, the batch size, and all that. So Bhavik would have told you a version of linear regression called stochastic linear regression. So I'll tell you what is batch one. I'll just do a thing. I'll just give a quick recap. So what happens is that essentially we compute the gradient over the entire data set, and in full linear regression, and then we update via the this update rule. Self dot weights is equals to self dot weights minus learning rate times the gradients. So that is the crux of this linear regression. um, the version that you have learned and the version that we'll be discussing today is the batch version of it. That is going to create the difference. So in the previous session, we would have told you that we are taking a single data point, and then we're computing the gradient for that point, and then we're working it out. But what we do now is we take a batch of points, okay, which is a subset from the entire data set, and then we compute the gradient over those points. And those gradients, they're just added up together, and this gives us a smoother estimate of the gradient, and then we update. So because of that, our updates are much more stable. So if you just think about it, what kind of functions do we need? We need something to initialize the class, okay, to define the hyperparameters for the experiment. We need something to compute the loss. We need something to update, and we need certain helper functions such as plotting functions so that we can see what is going on. So I have modularized my code accordingly. So the functions are init, initialize parameters, compute loss, batch gradient descent, predict, fit, plot loss, and plot regression line. So what the init function does is, whenever I declare this linear regression class, what happens is this init function gets called. So the learning rate, epochs, batch size, and all that are declared, and we declare cell dot bias and cell dot weights. In the initialize parameters, we initialize them as 0. They could be very well random, and I mean that would also work. Then we compute the loss, that is the mean square error. So predictions minus the actual value whole square, and we just sum that up. So that is the thing. And then we perform gradient descent. So what I'm doing is, so to say, firstly I'm initializing the parameters. Then there's a list called loss history. And for each epoch, what's happening is that I take a random batch, and this batch, well, we compute the gradients on them using cell.predict. So this cell.predict will first give me what is the this uh, W transpose X plus B, and this predict function will then be used to compute the updates. So these predictions are, so this is the gradient that I've calculated. So if anyone would remember, it was X transpose Y and X dot Y, and uh, like for bias, it would simply be predictions that we are taking. So that way we are able to define the gradient, the updates, and then we use the update equation to update it, and we store the loss in the loss history object. So now the predict function, it is nothing but just W transpose B, and fit function is calling the batch gradient descent function and giving me a list of how my function has updated in the meanwhile. And then there are these plot functions which will describe that, which will describe how I am up, like logging all these metrics. So I have just kept them as a helpful function. So they will print the loss. So to run this experiment, I am taking this. This is called random seed. So this is basically a method where we put a random seed into a random number generator so as to make our experiments reproducible. So I generate some random numbers x and y, and this is something like how my data looks like. So what I'm trying to do is I'm taking different batch sizes: 1, 4, 16, 32, and 64. And what I'm doing is I'm declaring a model, then I'm performing fit, and then I'm just showing the loss and the regression line. So as you would be able to see that when the batch size is 1, these what is happening is we're randomly picking a point and updating. I was discussing about our results that we had gotten. So if we are taking a certain batch size, and let's say the batch size is very small, essentially we are picking up a random point and updating by it. When we increase our batch size, we are able to take a better estimate. So that smoothens our, that basically gives us a better estimate, and that smoothens our update process. So as you would see for batch size 1, these updates are quite noisy. But as I'm increasing the batch size, the noisiness of this loss equation, it's decreasing. It's getting smoother and smoother. So as I go to a full batch, let's say I do 128 over here, and I'll just run all. This might take a few minutes to a few seconds to run.
Like also
this.
decrease the number of epochs, like because like they might be able to see it clearly if number of epochs are less.
Yeah, yeah, you're right. Okay, I'll do it for 100 epochs. Yeah. So I think, yeah, you're right. This is more visible now. So if we are increasing the batch size, we are getting a much smoother curve. Whereas if you see properly, if you so the line gets a bit noisy or a bit like unsmooth when you just decrease the batch size. So this is how it is fitting the line. We are getting more accurate predictions in well in the one with the larger batch size. So that is more or less the gist of it. So there were only 100 samples. So this is full batch gradient descent, 128.
What is batch size?
Okay. Okay, batch size. So batch size is the number of data points I'm taking. So a batch is basically a sample of points over which I'm computing the gradient. So earlier we were computing the gradient over only on one point, but now we are doing it. So basically we were doing it for one point, and now we are doing it for a certain like we are doing it for n number of points. So n is the batch size. Is that clear now?